I'm live. Cool. Right. Who doesn't like to be live? Google search. All right. So we left off yesterday learning the first three basic reaction types and balancing those. There we are. Okay. So again, we have synthesis, where we have two things coming together. Decomposition, where we break things up. And then combustion, where, well, how do we know something is a combustion reaction?
If it's fuel plus
Oxygen, and that always makes what?
carbon dioxide and
Water.
And water. Excellent. Yeah. So exactly right. So if it's a fuel, that fuel usually has carbon, hydrogen, and oxygen. So it just has carbon and hydrogen. If it's a fuel plus oxygen, and that's going to make carbon dioxide and water, we know we're looking at a combustion. Yes.
How can we tell that it's just fuel or anything like that?
Mostly habit, but in this class, like repetition, but in this class, if you see something plus oxygen makes carbon dioxide and water, it's a combustion reaction.
Okay.
Does that answer your question?
Yeah.
Yeah, so there's all sorts, realize we're just scratching the surface of all the chemical reactions out there, the five most basic. So I've tried to shield you from all the really crazy stuff. If you see something plus oxygen yielding carbon dioxide and water, you're looking at a hydrocarbon combustion. Cool? All right, so the next type of reactions are called replacement reactions. And in a replacement reaction, you have two ions, a cation and an anion. And those things are usually in an aqueous substance. Sometimes they're in gas phase. I'll show you when they're in the gas phase. And one thing replaces another thing. Okay? So you're going to have AB, and then D is going to come along, and D is in this case going to kick out B, or you'll have AB, and C is going to be by itself, and C is going to kick out A. So that is a single replacement reaction. And one of the coolest single replacement reactions you actually did when you made the silver ornament. We're going to do it again. So I'm going to take, where is my little, I need a little test tube. This test tube is too little. So when you did the silver, there we are. Oh, geez. When you did the silver ornament, you had some silver that was in solution, and you added to it some compounds that kicked the silver out of solution. We're going to do something similar right now. I'm going to put a little silver nitrate in this test tube. All right. There we are. Actually, you know what? That's better. Okay. So what I've got is some silver nitrate, AgNO3AQ. Now, once again, if you see AQ, you're not seeing silver nitrate. What are you seeing?
Water.
You're seeing the ions dissolved in water. Exactly right. So you're seeing the silver ions and the nitrate ions dissolved in water. So what you're really seeing is silver ions and nitrate ions. And to that, I'm going to add a piece of copper metal. Okay, run out of space again. The bigger I write, the faster I run out of space. So AgNO3 aqueous, and I'm going to add to it a piece of copper metal. And what's going to happen is this. the copper is going to say, hey, I am more active than silver. So I am going to kick out the silver. And there's a whole series of activities of metals right up there. The more active ones, the ones in the higher in the activity series, will be able to kick out the ones that are lower in the activity series. And if I had my little green bug, I could point at it, but I don't have my little green bug. But so copper is way up there, where it says react with oxygen, and it's 2 steps higher than silver. Silver is kind of behind the copper sulfate. There we are. There's silver, Ag. So since copper is more active than silver, it's going to go into solution and it's going to kick out the silver. You're going to do a lab next week, maybe next week, very soon, where you're going to have a solution of copper and you're going to kick out the copper with something else. But in this case, the copper is going to kick out the silver and it's going to form a solution of copper nitrate. Copper 2 nitrate. And that's going to be aqueous. And what's going to be left is silver metal. Solid silver metal. Is that balanced?
No.
Why do you say it's not balanced?
Because there's 6 oxygens and 2 nitrates on the right, and then half of that on the left.
Yeah, so you've got a single nitrate on the left and 2 nitrates on the right, so this is not balanced. So what I'd like you to do is take a minute or two and balance it. Well, I get my wire clippers. Snippy, snippy.
Go up. I just I have a practically
Wheel of names. Pick a good name, Wheel of Names.
Are they all more? What is
All right. Yes. You want this? Let's check that out. So 2, 1, 2, 1. So 2, 1, 2, 1.
Sorry, hold on.
Oh wait, 200.
No, sorry. 2, 1, 1, 2. Sorry.
2, 1, 1, 2. Okay. 2, 1, 1, 2. All right. So let's check our work. You've got 2 silvers here, 2 silvers there. Our silver is balanced. You've got 2 nitrates here, 1 times 2 nitrates there. Our nitrates are balanced. You've got 1 copper here and 1 copper there, and our copper is balanced. It is 2, 1, 1, 2. Okay, ready? Watch this. Copper into the boom. Oh. Well, it turns out sometimes things take a long time. So take a look at it right now if you can see it. You've got the copper wire chilling out in the silver nitrate. We're just going to leave that there for a while and talk about a reaction that is really exciting. And that reaction is the reaction of thermite. If you watch Breaking Bad, you heard about thermite. If you watch the really old Terminator movie, you learned about thermite. Thermite used to be used to weld railroad rails together. Because you have these rails and you put them down, and you're like, you notice the rails, if you've ever seen a railroad, they're really long. Like the rails that start in Los Angeles end in like St. Louis, they one continuous rail. Well, they can't move it like that, so they move sections of the rails and they have to weld them together. Well, nowadays they use gas welders or arc welders or plasma welders, but they didn't have that 150 years ago. But they did have chemistry. So what they do is they get these two rails really close together, and then they pack the gap with clay, and they put in between the gap this chemical called thermite. And what thermite was a compound of iron 2 oxide and aluminum powder. And they add these are all solids, solid. They add the iron 2 oxide and aluminum powder, then they get it really, really hot. And what would happen is the aluminum, being more active than the iron, would kick out the iron. And it would leave behind molten iron. So then you'd have your molten iron and aluminum oxide, not aqueous, solid, aluminum oxide. Mostly smoke, aluminum oxide. And that would weld the two rails together. Now, making thermite is exceptionally messy. So I do this ahead of time, because otherwise I'll just make a giant mess. So this is thermite. It's 13.5 grams of aluminum and 40 grams of iron 2 oxide. Is this balanced?
No.
Could you balance it? Yeah. Please do. Oh, hands can't. Hands. From downtown. Bullseye.
Yep. One, two, three. Yep. Oh.
1, 2.
Yeah.
Yeah.
1, 2, 2.
1, 2.
All the way.
Mine's not 1, 2.
Huh.
Nice. Well, I'm huge five.
Well, this is going to be interesting. I thought I had the cool magnesium sparklers, but all I have is these sparklers with the stick in the middle. So I'm hoping that they still work. You know the little sparklers, the little steel piece of metal, and the magnesium on the outside. So hopefully it's still going to work. All right. Any questions? All right. Wheel it again. 1, 2, 2, 1. Okay, let's check. 1 times 2 is 2 irons. 2 times 1 is 2 irons. Iron looks good. 1 times 3 is 3 oxygens. 1 times 3 is 3 oxygens. Oxygen looks good. 2 aluminums. 1 times 2 aluminums. Aluminum looks good. Okay, so just like before, we're going to go outside because this makes a tremendous amount of heat, a tremendous amount of smoke, and you want to be at least 2 meters away because it will throw sparks if done properly. If it works at all. And I'm just going to go stick this guy in there, and off we go. So just like before, if we're going to go outside, I need a smooth transition out and smooth transition in. Do I have a firefighter? Awesome. I'll get you the water bottle. Layla?
What?
Jace.
Who?
Fill this with water, please.
Okay.
There's a sink right behind you.
Yeah, that's him.
Jace is our firefighter.
Is that good?
Spark was there because of the high temperature to get the reaction going. Okay, that's cool. Do you see that ball right there? Definitely no. We're just gonna put some more water on it. But that ball, that is a ball of okay,
He's jinxed me.
I'll pull that.
You really did.
We'll let it cool down.
Oh. I was hearing a lot.
Why don't you see your
Back
bag
down.
down? You walk past me.
If anybody wants a ball of molten iron, it's waiting out there for you. Yeah, but it's really hot right now, so even though we poured water on it, it's probably still too hot to touch. But that's thermite. Pretty cool, huh? So the takeaway from that. Come on. There we go. The takeaway from that is iron was bound to oxygen, but aluminum, being more active than iron, got the chance and kicked the iron out. So the aluminum, here we go. The aluminum is right up here. Iron is down here. So if something is above something else in the activity series, the more active metal will kick out the less active metal. Sound good? All right. Oh, and the big one. Okay. Probably the single most dangerous thing we do in high school is reacting sodium. If you've ever seen sodium online, it reacts with water, reacts with air too, reacts with water pretty vigorously. And sometimes it reacts so fast it gets hot and explodes. Does that sound like something you'd like to see?
Yes.
Okay, in that case, yeah, we're not gonna, yeah, okay. So anyway, yeah, we'll definitely do fire. So what happens? Oh, by the way, this is totally cool. I love this. I got to share this with you. That guy is Dr. Rick Nafshin from Oregon State University. He was one of my mentors when I was there. I worked with him. And now he's like an internet dude. See, it says OSU. So that's him doing thermite in the lab. But he did those. Yeah, I worked with him when I was at Oregon State University. Pretty slick. Anyway, so we're gonna take some sodium metal. Are you paying attention? Because this is super important. And we're gonna react it with water, just plain old water. But something that a couple of you talked to me about yesterday is you're like, I can't get this reaction to balance, and it had water. Well, we like to think of water as H2O liquid, right? But chemistry doesn't like to think of water as H2O. They like to think of water, water, H2O. They like to think of water as HOH, HOH, where the hydrogen and the hydroxide can be easily separated. And that's how we're going to show water with the sodium here. We're going to show it as HOH, liquid. We're going to show the water as a hydrogen and a hydroxide. And what's going to happen when the sodium sees the water is it's going to see the hydroxide and like, yes, I am going to bond to that hydroxide. And I'm going to do that because hot sodium is way up there and hydrogen's way down here. So sodium is way more active than hydrogen. So it will actively kick out the hydrogen, leaving behind H2 gas and a solution of sodium hydroxide. And it's going to be aqueous because it's a solution. Okay? So the sodium's like, I am way more active than hydrogen. I'm going to kick out the hydrogen, leave behind hydrogen gas. Why do I have to do it H2 and not H?
Because it can't be.
It can be by itself because it is a diatomic, right? So it's diatomic, so it is the HA of Brinkelhoff. So the sodium's like, I am way more active than hydrogen. It's going to kick out the hydrogen and leave behind a solution of sodium hydroxide. Go ahead and balance that. And when you do that, come take a look at our previous reaction. Remember the copper wire and the silver that came out?
Oh, yeah.
So after you've balanced that, take a look at this while I set up our sodium and water, hopefully nobody dies reaction.
I'm just saying if the next time you're bigger explosion.
Cleaning.
It's good.
I just heard imagination. Keep putting it.
Nobody wants to take a look. You can see it. You can see the silver crystals. Also, the solution is blue. And what does a blue solution tell you? It tells us, if you understand chemistry, a blue solution usually tells you that there's copper ions present. So the copper went from the wire into the solution, and the silver came out of the solution and stuck to the wire. All right, sodium. So sodium is kept in mineral oil, and it's kept in mineral oil because it reacts pretty violently with air and water. So I'm going to pull out a piece of sodium. And I'm going to cut off a chunk. Just a wee chunk. Just a wee chunk. I'm going to pull that up. And then I'm going to bring this guy over. This is a giant graduated cylinder, half filled with water and half filled with mineral oil. By the way, which is the which half? Is the water on top or is the mineral oil on top?
Middle.
Down there. And so this is an acid-base indicator. So the water's down here and the mineral oil's up here, and that's an acid-base indicator. And what I'm going to do is I'm going to take my little sodium, and I'm going to drop it in here. Get on down there. because we are responsible. I'm going to put this back here. I'm sorry it's all scratched up. That's the best I could do. But what's going to happen is the sodium's, can you see this even behind the shield?
Yeah.
Okay. I know, sorry. I'll put it, it'll be in the fume hood. It's about to touch the water, and it touches the water, and it makes hydrogen gas. And it keeps touching the water and keeps making hydrogen gas. And it's nice and slow because we suspended it in mineral oil. But what we're going to do outside is we're going to take this reaction, which will go for hours. This will run for hours. We're going to do this reaction, and it's going to go like that. Okay. So we get our piece of sodium. Come on, piece of sodium. There we go. We've got our big old piece of sodium here. I'm going to fill this guy full of water. This is the trays they used to use in the 1950s. These things just won't die. I'm trying to make them die. I'm going to fill it with water. I'm going to put my sodium in the water. And then what's going to happen is first, the reaction is going to be exothermic, meaning it's going to release heat. It's going to melt the sodium. The sodium is going to dance around on a cloud of hydrogen gas, kind of like that is, only slower. And then if it gets really hot, it's going to explode. So I need you to be at least 3 meters away from it. All right. Can we handle this?
Yes.
Okay, let's go outside. This is too much water. Gage, can you grab this and take this outside? Just set it in the destruction zone out there. All right. So it's chilling out, reacting. If you can see that red color that's popping out under it, that shows the presence of sodium hydroxide. Huh. Not getting very. This usually catches fire by now. If it doesn't blow, put another piece in. Don't touch it. Don't go near it. Sometimes what you need is a bigger piece. Sometimes what you need is a bigger piece. All right, let's go back inside. Oh, watch this too.
He said, let's go inside. She ran. He got scared. He said, let's go inside. You were
Charlie Bird got scared.
On the move.
That's why. Yeah, we're like spraying. I have a next one. I blew my mouth. I like it. It's too much to break. Oh, really loud.
What?
Wow, you have the.
All right. Do what they say in science. The poison, the dosage is the poison. Just needed a bigger piece. All right. So those are single replacement reactions. One of the reaction types that we're going to do a lot in the next unit are double reaction types. So in single reaction types, something that is more, oh geez, I am muddy. Oh well, sorry, Mr. So in a single reaction type, a more active metal kicks out, or a more active thing kicks out a less active thing. In a double reaction, or a double replacement reaction, the ions switch partners. A and B plus C and D become, yeah, it's the presence of the hydroxide. A and B plus C and D react to produce A and D and C and D, or C and B. So what I've got in one of those test tubes is a compound called lead-2 nitrate. Lead-2 nitrate, and it is aqueous. And then I've got another test tube, and it's going to be aqueous. Right now it's a solid. And I'm going to use potassium iodide, and that's going to be aqueous. So right now they're solid. Remember, aqueous means dissolved in water. Let's get that stuff dissolved. Now that's aqueous. And now that's aqueous.
It's close. I don't know. Why is
It's totally safe as long as you don't need this. I'm going to hand it to you. Here's your test tube. Here's your test tube. So, okay, so these are two aqueous substances. Okay, so these are two aqueous substances, and what's going to happen is their ions are going to swap partners. The positively charged cation is going to swap with the positively charged cation, and the negatively charged anion is going to swap with the negatively charged anion. So what will happen at the end is a positive, negative again. So the lead here is +2, the nitrate's -1. The potassium is +1, the iodine is -1. So what's going to happen is the potassium and the lead will swap partners because they're both positive. And the nitrate and the iodine will swap partners because they're both negative. Make sense?
Yeah.
Okay. So what am I going to make? What's one of the things I'm going to make?
PBI.
Yeah. I'm going to make PbI2, lead-2 iodide. And what's the other thing I'm going to make? KNO3. KNO3. And here's the beauty. The potassium nitrate is going to stay aqueous, but the lead iodide is going to form a precipitate. Now it's not balanced. This is pretty easy to balance. You can just realize you need 2 iodines over there, so throw a 2 there. Now you got 2 potassiums. You need 2 potassiums over there. Throw a 2 there, and you're balanced. All right, ladies, stand up and show your class when decide who's going to pour and who's going to hold. You're going to pour one test tube and the other test tube. No, it's totally safe. That's why I didn't have them put glasses on. Otherwise, it'd be like, ah.
Oh.
That's cool. That's not as whack.
That's awesome.
That is pretty cool.
Like that.
Thank you very much. So, aqueous substances are usually colorless or very faint. This is not. In fact, if you're up front, you can actually see that there's solid particles that have already started forming, and the solid has started to settle to the bottom. The yellow stuff is the solid precipitate of lead iodide. You're going to do this in a lab in about 3 weeks. But that's what happens. The two aqueous substances form together to form a precipitate that falls to the bottom. Okay. Oh, I can't do those other two because we're out of time. That's okay. Any questions so far? All right. If you are comfortable with this stuff, give me a thumbs up. If you'd like to talk about this in any way, let me know. Put your hand up and like, I want to talk about this. All right, we're moving forward. So now you have all the reaction types you need to finish out your worksheets, and you have the balancing practice. We're going to talk about a couple more things. Wow. All right. Okay. Matt? I don't know. Here we go. Okay. No, you've got to be kidding me. Okay, come on. Come on, technology. There we go. Okay, so summary of our reaction types. Synthesis, two things together form one thing. Decomposition, they break apart. Single replacement, something more active kicks out something less active. Sorry, Luigi. And then double replacement, they swap partners. It's a me. It's a me, a stereotype. Okay. We've done a lot of practice, so I'm going to skip over this for time and talk about energy. Okay. This is probably a little new. We talked briefly about energy numerous times. Reactions can be exothermic or endothermic. I feel like I owe someone chocolate. I'll take it. Anyway. So reactions can be endothermic or exothermic. What does exo sound like?
Exit.
Exit, to leave, right? And what does endo sound like?
Enter.
Enter, inward. So if a system releases heat, we say it is exothermic. If a system has to absorb heat to happen or keep happening, we say it is endothermic. So systems that release heat are exothermic, and systems that have to take in heat to keep happening are endothermic. And the reason that's important is we can list the energy as part of the chemical reaction. Now, all reactions have to overcome what's called an energy barrier. So most of you know the whole point of having matches is so you can basically create heat. Is the burning of the wood an exothermic or an endothermic process? It's exothermic. And is the burning of the little piece of stuff at the end, when that goes whoosh, is that exothermic or endothermic? It's exo. They're both exothermic. They both release a lot of heat. But no matter how hard I try, I can't make it go. Because even though it's an exothermic process, it needs a little bit of energy to get going. A little bit of friction. The energy provided by the friction overcomes the energy barrier to start the reaction. So all reactions, even those that are very exothermic, still require a little bit of energy to overcome their energy barrier. What? I didn't know you cared. So the value of that energy that must be overcome is called the activation energy. So that's how much energy you need to overcome to get the reaction going. Even a very exothermic process like our thermite, you saw that giant fireball that released and it created molten iron. That thermite reaction releases a tremendous amount of energy, but it has a very high activation energy, which is why we had to use the sparkler to get it going. Question? Nope. No question. Any questions so far? All right, we have one more, I think one more concept to talk about, then we're done. If you're with me so far, give me a thumbs up. Awesome. If you have questions, wave your hand around. I got a question. No. Ready to move forward? Question.
So, like, how do you know if it takes energy to, like, if it's exothermic or endothermic?
Just by looking at it, I would tell you at this level of chemistry. So first year chemistry, I will tell you something is exothermic or endothermic, or you can do the lab and you can observe, like, it got really, really warm. If you're holding something and like it gets really, really warm, then the process is releasing heat, and you're observing it. If you're like, ooh, it got cold, then the process absorbed heat, and you're observing it. Okay. So at this point, I will tell you it's exothermic or endothermic, or you can just observe what happens in a lab, which you're going to be doing. If you take chemistry AP, you'll learn how to identify when something is going to be exothermic or endothermic. All right. Okay. Last thing we're going to talk about. If you have an exothermic reaction, like fire, then energy acts like a product. And we will write the amount of energy as a product. This unit, kJ, is kilojoules. A kilojoule is 1,000 dudes who did labs like 150 years ago. There's this guy named James Prescott Joule, and the unit of the energy, the joule, is named for him because he did some pretty cool stuff with thermodynamics, proving that energy can be converted into all sorts of crazy forms. So the basic unit, the simplest SI unit of energy is the joule, named after James Prescott Joule. If you want to know how to spell it, it's Joule. Joule. So in an exothermic reaction, we write the energy as a product. What do you think we do as an endothermic process?
Reactant.
Write it as a reactant. In an endothermic process, we write it as a reactant. Oh, I took it apart. Okay. I had a little device like this to break up water and into hydrogen and oxygen, and I was just, but I took it apart this morning. I didn't realize I didn't realize what I needed today. Anyway. If you run high voltage through water, we talked about this. You will make hydrogen and oxygen, and what this means is, remember how we talked about the mole ratio? 1 mole of this, 2 moles of that?
Yes.
Well, what this means is this. If I want to break 2 moles of water, I am going to need to use 571 kilojoules. So if I'm going to break 2 moles of water, because it's 2H2O, then I'm going to be required to use 571 kilojoules of energy. If I want to break 1 mole of water, I'm going to need half of that. Are you seeing? Are the gears turning? If I'm going to break apart 4 moles of water, I'm going to need twice that. If I'm going to break apart 20 moles of water, I'm going to need 10 times that. Is that clear? Okay, that's called energy stoichiometry. We're going to play with this quite a bit more. All right, I think you have everything you need for your practice activity. Any questions? Brandon?
So how do we tell, like, which like element is more active than the other? Is it just which one replaces the other?
That's an excellent question. There is something called an activity series. So when you are doing, so the question was, how do you know if one metal or one thing is more active than another thing? Look up the activity series. So you can use your activity series during your work, during tests, or whatever. Alexa, stop. Okay. So how do you know if something is more active? Look up the activity series. If you're in the front of the room, you can look at the wall. Otherwise, just look up the activity series. They're all going to be the same. Things that are above other things in the activity series are more active. So at the top of the activity series, you're going to find lithium, rubidium, potassium, sodium. Those are the most active metals. They want to be in compounds or in solutions. At the bottom of the activity series, you're going to find metals like gold and silver and platinum. Those do not want to be in compounds. They want to be pure metals. Non-active metals or low active metals want to be in pure metals. They're kind of like those of us who just want to stay home and watch football. I'm not active, stay home, watch football. The active metals, they want to be at a party. So lithium and sodium, potassium, like, I want to go to a party and hang out with other elements. The non-active metals are like, no, I'm cool, just staying home. I'm just going to stay home and relax, watch football, play Fortnite. Okay, questions? Other questions? That was a good question. All right, cool. So use the remainder of time. You do whatever you want to do. You now are fully equipped to do the worksheets and the skills tests.
Also, one of the skills tests that I realized that there's one equation that can't be balanced, and like the answer does not
Doesn't work.
Yeah, the answer does not look that they give us.
That is entirely possible, so we'll take it. One of these six nitrates.
We're seeing 1800 divided by 8.
Stop touching me like that, Carson.
You may stop.
Stop.
Yeah, so you're all the key walkers. And I'm like, yeah, yeah, you're right, like, I'm like, wait, you're serious? Okay, well, I think that's, what you say.
semester. You should come sit next to me. You're not the school over to that empty room. Because I don't want to move it. Chloe is not when people move it.
Who is this track?
Hate it.
You have black? What do we have to do?
Yeah.
Yeah.
I think so.
That's simulation. That'd be cool.
Were you just sitting and smiling?
I wasn't smiling.
Oh.
Was I?
He doesn't have emotion. He can't smile.
I thought I was gonna yawn, but then I didn't.
So what?
Yawn. I thought I was gonna yawn, but it didn't happen.
Who's got you on? Like
Me.
It's like a name.
Look at my.
You don't want to see me when I'm angry. Let's make me angry. Go for this one. Yeah, plug my phone. I woke up late and I fell asleep watching YouTube, and I didn't put my alarms. I don't know how I got school.
Fall asleep watching what?
YouTube.
YouTube. So, yeah, that checks out.
I woke up late because I didn't want to get up.
It's fair.
That also checks out. I
Because
woke
I
up
had
one time
horrible
with
sleep and I kept getting nightmares because my cat was in my room and sleeping on me.
a stupid cat.
I love my cat, but I'm allergic to cats, so I always have so much. So I have really bad sleep. And I'm just
The worst choices.
Well, I take Claritin, the knockoff, like the
yeah, so I
generic
have too.
constantly, just every day.
We got my mom.
But she's so, my cat doesn't she doesn't know how to clean herself, so she always just has hair on her, and she's a long-haired cat, and she sheds so much, and she has dandruff, and she can't clean herself. She never
You got the-
learned.
You got the worst of the worst situation going on.
I know. And I'm dying
You
in my
screwed
bed,
up so bad.
and she's just sitting on me crying, and I feel so bad. I can't get up.
That's
Death animal. Go away, torturous animal.
I'm a furry.
Yeah, my mom coaches cats, and we got some Siamese. But allergic people aren't as allergic.
Siamese?
Yeah, I think so.
Really? I didn't do that.
You
I have a
should
Siamese.
They don't give out like the protein or whatever. So
Things you learn.
most
I-
people.
Siamese ragdoll.
You're
She's a little crazy.
Okay, so before you work on your calorimetry simulation, I need to know how you are doing with the exercises.
I didn't understand a lot
I did the first one, and
Yeah.
every time I picked an option, it was the other one.
All right. Then let's talk about it.